There have been a number of theories batted around about the causes or processes that contributed to the collapse of the Surfside condominium. Several of those are geological phenomenon that many people may simply never heard of or been familiar with, specifically the potential effects of sea level rise, subsidence, and saltwater intrusion. So I've created a short video that describes what those processes are and how they may have or may not have contributed to the failure of the condominium. My name is Randall W. Parkinson. I have a PhD in marine geology and geophysics from the University of Miami. I'm a registered professional geologist in the state of Florida since 1988, and I am a coastal geologist and research associate professor at Florida International University in Miami, Florida. So let's begin. So the phenomenon that have been discussed as a possible cause of the Surfside condo collapse, there are really three different phenomena. One is sea level rise, the other is saltwater intrusion, and the third one is subsidence. So we'll point out that the location of the condominium is along the Atlantic Ocean, so it is subject to the effects of marine and coastal conditions, which is certainly why a sea level rise and saltwater intrusion have been mentioned in discussions about the origin of the failure. So let's begin with changes to the caused by sea level rise. So let's just start at time one, maybe when any building was constructed, and we're looking at a cross section of the shoreline here. So here's land, Miami, Dade County, and then the sea. And if you look beneath that, what you'll see is here's the land, and under the land is fresh water, is groundwater. And then that eventually transitions into seawater. So if a condominium is constructed and they have pilings and so forth that penetrate downward, they may, at the beginning, penetrate into and reside within a freshwater environment. But in time two, say 40, 50 years later, sea level has risen. And what this does is it takes the original shoreline and moves it in, but it also changes the location and geometry of the freshwater lens. So here is the boundary of the lens in time one, and here is the boundary of the lens after sea level has risen. And what you can see is that boundary between freshwater and saltwater has moved, and now the lower portion of the piling or pilings are within a saline water environment. And of course, if the pilings were constructed, designed, and so forth just to consider freshwater conditions, then it's possible that this change from fresh to saline groundwater or waters will affect the properties, the structural properties of the pilings. And the first one that comes to mind is simply corrosion, reinforcing rod corrosion, and concrete spalling. So here's an example of a pier, and here is sea level. And what you can see is these cracks and so forth are caused by the interaction of the iron rebar and the saltwater environment, which causes the rebar to corrode. And as it corrodes, it expands and it basically breaks up the concrete and structures, in this case holding up probably a walkway or a pier or something like that. So that's one potential cause of the failure. A second one is saltwater intrusion. So again, we're at a cross section. Here's the land surface. Here's the ocean, the shoreline. And again, beneath the land, there's fresh water. And here again is that saltwater wedge that's associated with sea level, right? And let's just say hypothetically that sometime later, we put a well in, all right? And the well is pulling water from the groundwater table. And as it does so, it pulls the groundwater down at where the well is pulling in the water and creates a cone of depression because it's sucking out more water than can be replaced by freshwater flow. But there's also what's called a cone of ascension. So the base of the freshwater ledge is pulled upward. And as a consequence, you can see a piling that was put in at time 1. If a well or wells are put in around the piling or pilings, it can change the environment from freshwater to saltwater. And then again, if the piling was not designed for this new situation, it can generate corrosion, spalling, and a decrease in the performance of the pilings, so saltwater intrusion. So the third geological phenomenon is subsidence. And subsidence is just simply the land's surface lowers or subsides over time. And this can be caused by fluid withdrawal or surface loading, and is expressed in distance over time, for example, inches per year. So in this example, this is a cross-section of, let's say, the substrate and soils and so forth. And here is a building and a piling that penetrates much deeper and, in fact, into a zone where there's no compaction or compression of the soils possible. And here's another one with a shorter footer or foundation. And the land simply subsides because either just the weight of the things that have been placed on the surface just compresses the materials. In other cases, it can be because fluids have been withdrawn, like oil or gas or groundwater, and those fluids or materials are within the void spaces of the soils and sediments, and that helps to keep everything sort of dilated. And if we remove those fluids, then the soils may in fact compress or compact to fill the spaces left by the fluids that have been removed. So here we see in time 2 now, this same building, which had a very deep foundation or footer, it stays up at the original elevation and the land subsides around it. In the case of a building that has none or a shallow footer, it compresses downward and subsides along with the soils. So there's the third. And here's a very interesting example from the San Joaquin Valley there in California. 50 years of subsidence, 50 feet. So here was the land surface in 1925. Groundwater withdrawal lowered the land surface to this elevation in 1955. And then by the time this picture was taken, it had dropped over about 50 feet, or 1 foot of subsidence per year. Now, again, just to remind folks about how this can affect buildings, we can look at a building with a deep foundation, a shallow foundation, a road with no foundation, and a building with no foundation. So here's the original surface. And here is the present surface. So the deep foundation, it moves just a little bit. Here was where it was built, and it moves a little bit down because of the deep foundation. A building with a shallow foundation moves further downward in response to subsidence because its footers, if you will, just aren't deep enough. A road, when done, just follows the land surface downward. A building, a large building, which has a weight to it, it actually subsides downward and into the present ground surface, so the most. So depending on the foundation, different subsidence rates can occur under similar conditions. And as an example of this, this is at a hospital in China, and this is an aerial photograph. So these are the tops of buildings here, right? And here's a street, perhaps a park, and so forth. And these colored dots are symbols for various rates of displacement or subsidence measured in distance per time. So where you see the red dots, we're looking at displacement or subsidence of 100 millimeters per year to 40, all the way down to hardly any at all, 5 millimeters per year. And so you can see this tall building here is subsiding quite quickly over time from an elevation of 0 to minus 250 millimeters over 3 years there. In other cases, you can see where there was little or no displacement. Here's a yellow dot, so that's about 10. There's the displacement. The steepness of these reflects how quickly it is subsiding, with the steepest being very fast and shallow being less. But the point is, you have all these buildings next to each other. The subsidence measured is not the same, because it could be geological phenomenons occurring there, different kinds of soils underneath them, could be just due to the weight and design of the buildings, a variety of factors which I have addressed earlier. And certainly if these buildings are attached and one is just being displaced or subsiding at one rate and another at a different rate, then there's going to be stresses introduced at that connection, and certainly between the two buildings. So, brief overview of the phenomenon, the geological phenomenon that have been discussed in light of the catastrophic and tragic failure of the condominium at Surfside. And here is some contact information for you. Thank you.